with the lecture on genetics for, I don't know, maybe half an hour or so. And then what today's laboratory is actually just genetics worksheets, working some genetics problems. Here in lecture, I've been sort of spewing a lot of theory at you about how to do Punnett squares and how to do this and how to do that, but we haven't got a lot of hands-on practice on it yet. That's what today's lab and Wednesday's lab are going to be all about. But wouldn't you know it, for some reason, my computer doesn't want to connect for some reason, so give me just a moment to try to figure that out. There. Okay, well, I guess that'll have to do then. Okay, so in the lecture hall, I just got done telling you about recessive genetic diseases. And this is the most, well, maybe I should just say, genetic diseases, remember, are any time a person is missing some important gene, a gene that's necessary for proper health, proper functioning of the body. And most times, the genetic disease is caused by inheriting two recessive alleles for a certain gene, a gene for some important protein. And I've been using the letter Q to represent this. So if a person is born with this as their genotype, whatever this enzyme Q is, they don't have a functional copy of it, because remember, most of the time the recessive allele is for a non-functioning version of that gene. And so they're missing this important enzyme. Whereas if a person is like this, then they have a functional copy of the gene for that enzyme. So they will have the enzyme, and they'll have their proper metabolism. But there's a small group of what are called dominant genetic diseases. And in dominant genetic diseases, it's still caused by a mutation in the normal gene, but what's happened is the mutation has given the protein a new function or an altered function. And that's an extremely rare thing, because as I've been emphasizing, mutations are random events where some random change in the gene has caused the mutation. And most of the time, if you randomly change something, you're just going to stop it from functioning. If I open my computer and stick a wire in some spot where it's not supposed to be, that's a random change. My computer's going to not function. But occasionally, just by random chance, every now and then, if I do that, I might actually give my computer some new function that it didn't have before.
So in evolution, that's completely random? So many species will be born into a generation, and then some outer environmental factor will only allow the ones that have a certain random genetic mutation to survive?
Well, I guess I would say that in terms of which nucleotides and which genes are mutated, that is random. If I stand in the sunlight and let the ultraviolet radiation mutate the DNA in the cells in my skin, which nucleotides in which particular genes get hit by those UV photons, that's completely random. But once the mutations occur, then evolution will then sort through them, so to speak, and the ones that harm the species eventually get kicked out because it harms those individuals who have those genes, but the mutations that are beneficial build up in the species, they accumulate in the species because those help the individuals survive who have them, and then they pass that trait on to their offspring. Is that sort of the question you were asking? Okay, yeah, it's more like the mutations themselves are random, and then evolution looks over all the random mutations and chooses the good ones is a good way to think about it. Anyhow, so most mutations just stop the protein from functioning, but every now and then you'll get a mutation that will give the protein a new function, or in some way seriously alter its original function. And so that's a pretty rare thing, but it does happen, and when it does, you get what's called a dominant genetic disorder if that new function is actually somehow bad for the body. You get a functional protein, but it's doing something that we should say the protein has a new function, but that new function is not something that benefits us. And a good example of that is something that's called Huntington's disease. In Huntington's disease, which is, as I said, one of these dominant genetic disorders, it causes a degeneration of the nervous system. The neurons start to die, but for some reason, it doesn't become active until middle age, and I'm not sure exactly why there's that long delay. So the person will have pretty much no symptoms throughout the first half of their life, and then in their late 30s or early 40s, their ability to move their body in a coordinated way starts to deteriorate, and eventually it's a fatal disease. They don't have a cure for it yet. Now, there's something kind of interesting about these dominant genetic diseases. Because they're so rare in the population, if you find an individual like the woman here who has the genetic disease, you should always assume that person is heterozygous for it. Remember, in this case, it's the dominant allele that gives you the disease, and the recessive allele is the one that doesn't give you the disease. So, assuming that nobody in here has Huntington's disease, then everybody in the room is little q, little q. We don't have the allele that gives you the Huntington's disease. Anyway, if a person does have a dominant genetic disorder, you should assume they're big Q, little q, and not big Q, big Q. Why not? Well, because this allele is so rare, the chance that you would get it from both your parents is just almost astronomically small. Maybe to make an analogy, one time I found a $20 bill, and that's a pretty rare instant. What would be the chance of me finding two $20 bills in one day? You know, that's just astronomically small. And so anyway, anytime someone has the dominant genetic disorder, just assume that they're big Q, little q. And people who don't have the disorder have to be little q, little q. Here are some other examples. Oh, actually, before I leave Huntington's disease, here's a little background about it. You don't have to know this gentleman's name, but his name was Woody Guthrie. He was a folk singer in the 1930s, really famous. And he had Huntington's disease, so he died in his middle ages of it. If we assume what I say was correct, so he must have been big Q, little q for the disease. And his wife did not have the disease, so what was her genotype? She had to be little q, because remember again, it's the dominant allele that gives you the disease in these. So here they are. What's the probability that any kid of theirs will have Huntington's disease? 50%, or 1/2, right. If you fill in the Punnett square, we expect half their kids to not have Huntington's disease, and half their kids to have Huntington's disease. And as it turns out, they had two children. The son was named Arlo. He was a musician also, and I don't know anything about the daughter. What's kind of interesting is, so they were probably born in the 1950s or so, and at that time they really didn't have anything as genetic testing, and so the kids were not sure if this was their genotype and they would not die of the disease, or if this was their genotype and they can expect to die in their late 30s or early 40s of the disease. Well, just about the time these kids were hitting middle age, the genetic tests for this disease were invented, and so they were offered the choice: do you want to take this test to find out what your genotype is and to know whether you're going to die in a few years or not? And I thought, wow, that's kind of an interesting predicament to be in, because on one hand, if it was me, I'd sort of like to know if I was going to die in a few years, so you could make arrangements and get your affairs in order. But at the same time, I know for myself that I'm happiest if I'm optimistic about the future. And if someone said, no, you're going to die of this horrible disease in a few years, that would be kind of a downer, so to speak. I don't know, something to think about. Would you take the test if someone could give you this option? As it turns out, both kids took the test, and they got lucky. They were both big little q, so they did not have it. But on sheer probabilities, if there were two kids, you would have not think that one of them would have been big Q, and the other one would have been little q. All right, just a few more examples of dominant genetic diseases. There's one called polydactylism, which is an extra finger or extra toe. I'm not sure exactly what the enzyme is that operates here, but somehow it's carrying out some function that it normally doesn't, and it ends up putting some extra digits on the person's hands or finger or toes. And there's a type of dwarfism called achondroplasia. And there's different things that can cause dwarfism. Some of them are recessive, but this particular type of dwarfism is a dominant characteristic. Sound alrighty? Okay. Now, if a person knows that there's some sort of disease that runs in their family, they're often curious to know what their own genotype is. You might want to know if it's Huntington's disease, am I going to get it? Or you might be interested in knowing if you're a carrier of the disease, which, remember, means you're heterozygous for it. So you might have a chance then of passing it on to your children. And so there are people whose job it is to analyze people's families and try to figure out the genotypes of everybody, so members of the family can figure out what their genotypes are and to know if they're carrying the disease or not. And these people are called genetic counselors, and what they construct is a type of chart for the family called a pedigree analysis that shows the genotypes of the family members. And this is something you'll be doing in today's lab. In these pedigree charts, circles represent females and squares represent males. And if the person does not have the trait, and if we're talking about disease, you think of not having the disease, it's an open circle or open square. And if the person does have the disease, it's a filled-in circle or a filled-in square. And let's go through one of these just to show you how you can fill in the genotypes. And maybe I can show it here also. Let's see. Okay, so here is a couple that's going to have children. And here are their kids. So this is a review. How many boys and how many girls do they have? 2 boys and 1 girl. Good. All right. And one of the boys has the disease. All right. So the first thing we should think about is, well, is this disease dominant or recessive? And just to work through the possibilities, let's think for a second. Well, could it be a dominant disease? All right. So if it's a dominant disease, which, remember, means the dominant allele gives you the disease, do we know the parents' genotypes? Well, do the parents have the disease? No. And so what has to be their genotype? Little q, right, because if the dominant allele gives you the disease and you don't have the disease, then you don't have the dominant allele. And so if it's a dominant disease, we know that they have to be little q. As a matter of fact, anybody who doesn't have the disease has to be little q. So what's this girl's genotype have to be? And how about her brother here? And how about this person? Big Q, little q, apparently, but then we get the question, where did this big Q allele come from? You get your alleles from your parents, but no parent has the big Q allele, so it doesn't work. If it's a dominant genetic disease, you can't have any of the kids having it unless the parents have it. And so I'm saying, just looking at this, we know that the disease has to be recessive. There's just no way it can be dominant, otherwise the parents would have had it. And so that's one of the important take-home messages from here. Anytime you see children showing up with a disease, but neither of the parents have that disease, you can immediately rule out that it's a dominant disease. Or some people say dominant diseases can never skip a generation. Skip a generation meaning the kids have it and the adults don't have it. So we know it's not a dominant disease, so let's get rid of those genotypes that we had there. So that leaves us the possibility it's a recessive disease. If it's a recessive disease, meaning you get it when you're little q, who on the chart do we know their genotype? For sure.